Hi, let us see how to determine the inverse Fourier transform of the given spectra using partial fraction techniques, right? So before getting into the problems, let us revise. X of t gives x of j omega upon application of CTFT on x of t. Same thing from x of j omega, it is possible for me to obtain x of t using inverse Fourier transform. The formula for inverse Fourier transform is also given 1 by 2 pi integral minus infinity to plus infinity x of j omega into e power j omega t into d omega. So this is the usual method of obtaining Fourier transform and inverse Fourier transform. So given x of t, obtaining x of j omega is called forward CTFT, or it is called as CTFT in general. Given x of j omega, obtaining x of t time domain signal from the spectrum is called inverse Fourier transform. It is called as CTFT inverse. Okay, you must understand these two in general before proceeding with the new problem. The problem is given like this: x of j omega is equal to 3 times j omega plus 14, the whole divided by j omega squared plus 7 into j omega plus 12. In such a situation, it is required to calculate what is the corresponding x of t. Right. Let me apply the partial fraction technique to find out the inverse Fourier transform of it. So before proceeding it further, I just write x of j omega. X of j omega is equal to 3 times of j omega plus 14 whole divided by j omega squared plus 7 j omega plus 12 can be rewritten as j omega plus 3 into j omega plus 4 factors of the denominator polynomial is generated. Factors of the denominator polynomial are generated. So using partial fraction, it is possible for me to write this, the entire given x of j omega into 3 times of j omega, numerator remains the same, plus 14 the whole divided by j omega plus 3. I just rewrite it again, multiplied by j omega plus 4. There are two factors. Let me write them as a divided by j omega plus 3 plus b divided by j omega plus 4. So in such situations, if you have to calculate the value of a, right, what should I do? I have to take x of j omega multiplied by the factor, right, which is available in the denominator of a, and I have to substitute j omega is equal to minus 3 everywhere. So in this methodology, I just write like this: 3 j omega plus 14 whole divided by j omega plus 3 multiplied by j omega plus 4 multiplied by j omega plus 3, and I just want to replace wherever j omega is there. At last j omega will all be replaced by minus 3, right? This is the method of finding out the constants involved in the partial fraction. So j omega plus 3 will get cancelled. So in the remaining equation, when we substitute j omega is equal to minus 3, this equation turns into 3 multiplied by minus 3 plus 14 whole divided by minus 3 plus 4. So that gives me the final answer as 5. So the first constant a is calculated using this method. Similarly, now I want to calculate the constant b. So to find out b, I should again take x of j omega, multiply x of j omega by the other factor j omega plus 4, and I have to replace j omega wherever it is available. After simplification, j omega will all be replaced by minus 4. If I start doing it, I will find out 3 times of j omega plus 14, the whole divided by j omega plus 3 is one of the factors, the other factor is j omega plus 4, and I have to find out the value of b, for which I need to multiply the factor which is available in the denominator of b in the partial fraction technique, and I have to cancel out the common terms. I have to find out, and I have to replace wherever j omega is available by minus 4 thereafter. So when you do this, you will get minus 12 plus 14 in the numerator. The whole divided by j omega is replaced by minus 4 plus 3. So you will find out now this time it is minus 2. Yes. So the constant b is obtained as minus 2. So I'll go back to the original expansion what I planned, except j omega should have been written as a divided by j omega plus 3 is one of the factors. It is j omega plus 3, right? And the other one is plus b divided by b is minus 2 the whole divided by j omega plus 4, right? So this can be furthermore, right, rewritten as, how will you rewrite it? Rewritten as x of j omega is equal to, I'll once again present it in the new screen, 5 divided by j omega plus 3 minus 2 divided by j omega plus 4 is available. If you take inverse Fourier transform, apply inverse Fourier transform for continuous time signals on both the sides of the above equation, I'll find out x of j omega upon process with the help of inverse CTFT. I'll obtain x of t, but when I take inverse Fourier transform of the right hand side terms, I'll find out the 5 divided by j omega plus 3 is the first term. The second one is 2 divided by j omega plus 4. So when we take the constant 5 outside, and if the Fourier transform is applied, inverse Fourier transform is applied only on 1 divided by j omega plus a, that is 3 here, and if I take 2 outside, and if I apply Fourier transform, inverse Fourier transform only over the term 1 divided by j omega plus 4, now you can notice that the expression will get reduced to the form 5 times of e power minus at. So here the a is considered to be 3 into t into u of t minus 2 times of e power minus 4t u of t. Why? Because you should remember one of the important identities, e power minus at u of t upon application of Fourier transform CTFT. This results in, what is the result of this Fourier transform on e power minus at u of t? That is equal to 1 divided by j omega plus a, isn't it? A plus j omega. So in this similar situation, if you start simply comparing with the above two relationships, right, j omega 1 divided by j omega plus a should be considered as e power minus at u of t in time domain. That is how x of t is simply obtained as a result, as 5 into e power minus at u of t minus 2 is constant. Upon application of inverse Fourier transform on 1 over j omega plus 4, now you will get e power minus 4t, right, e power minus 4t u of t. Yes, it is over. Shall I go to the next problem? So if you want, I am ready to even get into a similar situation like this. You know, I have got an expression like this, x of j omega is equal to j omega plus 7 is in the numerator. Let me obtain j omega plus 3 in the denominator, and that to the whole squared. So by using partial fraction, it is decided to find out x of t. So the question is, you have to find out the corresponding x of t using inverse continuous time Fourier transform, but this time you have to use only partial fraction technique without applying the formula. You have to just proceed with. So let me start with the solution. The solution is simply taking x of j omega, what is given in the problem as such, it is j omega plus 7 divided by j omega plus 3 the whole squared. Yes, it is available. Now in order to simply rewritten this case, a divided by j omega plus a 3 the whole squared plus constant b divided by j omega plus 3. Yes, if we can obtain this, I can find out the constant a. A can be obtained by simply taking the whole expression x of j omega plus 7 divided by j omega plus 3 the whole squared multiplied by, what is to be taken, multiplied by j omega plus 3. What is available as the denominator polynomial under the constant a should be written, and you have to at last after simplification replace j omega by simply minus 3, isn't it? When you substitute that, j omega plus right, I just cancel out the j omega plus 3 the whole square, j omega plus 3 the whole square. Now you will see the result simply remains with j omega plus 7, isn't it? When you substitute j omega is equal to minus 3 into this equation, you will find out that minus 3 plus 7, which gives me the constant value as 4. Right? Think about substituting back into the expansion. Before doing that, let me determine the constant b also. What is b? How will you find out b? For finding out b, the best method that is suggested here is you have to take j omega plus 7, numerator divided by j omega plus 3 the whole square, as usual, multiplied by j omega plus 3, which was the whole square, right? Where you have to simply take the differentiation of the entire expression with respect to j omega once, and you have to replace at last j omega is equal to minus 3 anywhere inside. So I have to simplify this. J omega plus 3 the whole square, j omega plus 3 the whole square will get cancelled. So what remains is only d by d j omega. With respect to omega, I have to differentiate once. J omega plus 7 remains. And after doing everything, you have to simply replace j omega by minus 3. So now you can find out that this will be simply equal to, how will you do that? When you differentiate it with respect to j omega, you will get the constant as, what is the constant? The constant value is 1 for the first term. When you differentiate it, you will get 1. 7 is a constant, so it is not a function of j omega, so it cannot be furthermore simplified. And at last you have to replace wherever j omega is there in the expression by minus 3. There is no j omega term, so I will write the constant value as b in this expression. So now I determined the constants a and b. So when I get back to the equation, what was originally written by me, j omega through partial fraction, a is 4 divided by j omega plus 3 the whole squared is available, plus the constant b divided by j omega plus 3. Yes, you will be able to get it. Now if you apply inverse Fourier transform, let me write it like this, apply CTFT inverse on both the sides of the above equation, you will find out that upon application of inverse Fourier transform on x of j omega on the left hand side, you will get x of t, whereas the Fourier transform of the inverse Fourier transform of the entire expression 4 on the right hand side, j omega plus 3 the whole squared is available, plus 1 divided by j omega plus 3 is available. Yes, is this okay? Now I just want to take you to an important portion where you should remember some of the identities. Fourier transform of e power minus at u of t is to be remembered as 1 divided by j omega plus a. Result, it can be easily proven. It is also another numerical problem as far as Anna University portions are considered. So Fourier transform on t into e power minus at u of t will simply result in 1 divided by j omega plus a the whole square. You must remember these two identities. If you keep these two items in memory, then it is possible for you to rewrite the entire expression in terms of t, the previous one. I'll write it again. X of j omega, what is available? X of j omega is equal to 4 divided by j omega plus 3 the whole square plus 1 divided by j omega plus 3. So upon application of inverse Fourier transform on both the sides of the above equation, x of j omega is equal to Fourier inverse transform applied on the entire expression j omega plus 3 the whole square plus 1 divided by j omega plus 3. correct? When we apply inverse Fourier transform on x of j omega, it results in x of t, whereas inverse Fourier transform of 4 divided by j omega plus 3 the whole square should be considered as 4 into inverse Fourier transform of 1 divided by j omega plus 3 the whole square plus Fourier inverse transform of 1 divided by j omega plus 3. So by making use of the known identities, 4 into t into e power minus at, so minus 3t into u of t is the inverse Fourier transform of the first term. The second one will be simply e power minus 3t u of t. So x of t is already available with us like this. It's readily available. Right? So you must know how to apply partial fraction so that the known identities can be easily included in our portion like this. This is okay, then we shall proceed further. Right? I'll continue with the next problem. Next problem is obtaining the result of convolution of x1 of t and x2 of t. What is the result of x1 of t convolved with x2 of t? Where x1 of t is given as e power, say for example, I have minus 2t u of t and x2 of t is equal to e power, say minus 6t u of t. You have to determine the result of convolution, right? But you have to use Fourier transform. Use CTFT and its properties to obtain the result of convolution. So let me start with the solution. I assume that Fourier x1 of t is the first signal, and upon application of Fourier transform, continuous time Fourier transform meant for continuous time signals, x1 of j omega is obtained as the result of it. I have x2 of t with me. Let me apply the Fourier transform on it. I'll obtain x2 of j omega. Right? This is the known fact. But what about the convolution of x1 of t with x2 of t and applying Fourier transform on the result according to the convolution property? It need not be done in the way mentioned, like taking x1 of t, convolving it with x2 of t, and then over the result of convolution applying Fourier transform need not be carried out. You can simply take x1 of j omega, right, and x2 of j omega, you can simply multiply them. It is equivalent to applying Fourier transform on the result of convolution of x1 of t and x2 of t. That is the convolution theorem. So I'll put it like this. I have the result x of j omega, which is the product of x1 of j omega with x2 of j omega, right? So if you ask me to find out what is x1 of j omega, according to the procedure already given, Fourier transform of x1 of t is called as x1 of j omega. What is x1 of t? E power minus 2t u of t is x1 of t, isn't it? This is what given as x1 of t. Please recall from the previous slide. Multiplied with Fourier transform of x2 of j. What is x2 of j omega? Fourier transform of x2 of t. What is x2 of t? x2 of t is simply e power minus 6t into u of t. Please recall. Right? If you want to see the statement of the problem, you can notice x1 of t is given, x2 of t is given. So using x1 of t and x2 of t, we have to find out what is x1 of j omega and x2 of j omega. Using those results, we must find out the Fourier transform of the result of convolution of x1 of t and x2 of t. So this is how it is written. So Fourier transform of e power minus at u of t is known as 1 divided by, right, j omega plus a. A is 2 here, multiplied with 1 divided by Fourier transform of e power minus 60 u of t. How will you obtain it? You have to use the formula 1 divided by j omega plus 6. Correct? Now, the result x of j omega is the product of x1 divided by j omega plus 2 multiplied with j omega plus 6. Right? So, when you expand it, it will become 1 divided by j omega plus 2 multiplied with j omega plus 6. Right? When you want to use partial fraction method, you have to write it like this: a divided by j omega first factor plus b divided by j omega plus 6. So what we have to do? We have to calculate or determine the constants a and b in this equation. So in the statement of x of j omega, a divided by j omega plus 2 plus b divided by j omega plus 6. If you ask me to calculate or determine what is a, I should take the entire expression j omega plus 2 multiplied with j omega plus 6, right, multiplied with j omega plus 2, and upon simplification you have to replace j omega is equal to minus 2. If I do this, surprisingly I will find out j omega plus 2 will get cancelled. Now 1 divided by j omega plus 6 remains. When I substitute j omega is equal to minus 2, the result will become minus 2 plus 6. It will be 1 over 4, isn't it? 0.25. Similarly, if you ask me to find out the value, determine the value of b, I should say b is equal to 1 divided by j omega plus 2 multiplied with j omega plus 6 multiplied with j omega plus 6. Upon simplification, you have to say j omega is equal to what will you replace? J omega is equal to minus 6 in your result. So when you cancel out j omega plus 6 will get cancelled. 1 over j omega divided 1 over j omega plus 2 is available as a resultant, where j omega is to be replaced as minus 6. So 1 divided by minus 6 plus 2, that gives me minus 1 by 4, minus 0.25. Agreed? So I'll now go back and say x of j omega is now written as 0.25 divided by j omega plus 2 minus 0.25 divided by j omega plus 6. Right? If you do like this, now if you apply inverse Fourier transform for continuous time signals on both the sides of the above expression, you will find out that Fourier inverse transform of x of j omega result in x of t, and inverse Fourier transform of 0.25 divided by j omega plus 2 will result in 0.25 e power minus 2 t u of t, minus inverse Fourier transform of 0.25 divided by j omega plus 6 will give me 0.25 e power minus at u of t minus 0.25 e power minus 60 u of t is available. This is what known as x of t. Right? This x of t is available like this. Right. Now, I just want to remind you, we started with a simple calculation like this. Right? Fourier transform of x1 of t gives me x1 of j omega. Fourier transform of x2 of t gives me x2 of j omega. With these two assumptions, I just proceed with Fourier transform of the convolution of x1 of t with x2 of t is equal to the product of x1 of j omega and x2 of j omega. Actually, in this problem, we assumed that x1 of j omega and x2 of j omega, the product is equal to x of j omega. So if I apply Fourier transform, if you go back to the last slide, I'll put it like this. X of j omega is simply the product of x1 of j omega and x2 of j omega. So when I do inverse Fourier transform on both the sides, right, x1 of j omega multiplied with x2 of j omega, it means that I'm applying inverse Fourier transform on x of j omega. So when you ask me to rewrite, I'll write it like this: x of t, which is actually the result of convolution, isn't it? x1 of t convolved with x2 of t, right? Assuming that, and if I apply Fourier transform on both the sides, x of j omega is the result. If I apply Fourier transform on the result of convolution, surprisingly, according to the property, it was written as x1 of j omega multiplied with x2 of j omega, isn't it? Now, so you can just recall x of t, the Fourier transform is, what was the Fourier result? It was in our case 0.25 e power minus 2t u of t, isn't it? Minus 0.25 e power minus 60 u of t, right? What is x of t? X of t is actually the result of the convolution of x1 of t convolved with x2 of t, isn't it? So the result of convolution is written as 0.25 e power minus 2t u of t minus 0.25 e power minus 60 u of t, correct? So this is the result of convolution. We determine the result of convolution using this convolution property. I am ready to even say one more point about it. When I have x1 of t, what is x1 of t? x1 of t is e power minus 2t u of t. Its Fourier transform results in x1 of j omega, which will be equal to 1 divided by j omega plus 2. Similarly, x2 of t is e power minus 60 u of t. The Fourier transform is actually, what is x2 of j omega? 1 divided by j omega plus 6. The result of convolution, if you want to calculate what you should do, take those two results. Which results? The results of individual Fourier transforms, and multiply them, and then over the result apply the inverse Fourier transform on the result. So the result of inverse Fourier transform of x1 of j omega and x2 of j omega, 1 divided by j omega plus 2 multiplied with 1 over j omega plus 6 gives me a result of, right, 0.25 into e power minus 2t u of t plus, sorry, it is actually minus 0.25 into e power minus 60 u of t. So is the result of this convolution, right? The result of this convolution. Is this okay for you? Shall we wind up our class with this? Thank you. But 1 minute. Before stopping this, I just want to give you some problems so that you can proceed as your assignment work.